My task today, the way I saw it, was to try to explain, to tell you something about p-adic Hodge theory, or Hodge theory of p-adic varieties. It's an area which Gerd Faltings influenced greatly, and it's also an area which is very important for modern arithmetic geometry and number theory. So I'm going to start with saying a few words about the p-adic world in which we are working. So p-adic numbers over which our varieties will be defined. So I start with rational numbers. So let's look at rational numbers. And on rational numbers, we have the usual Archimedean norm, but we also have p-adic norms. And the theorem of Ostrowski, an old theorem, tells us that these are all the norms that we have. Non-Archimedean norm means that we don't have the usual triangle inequality. We have a stronger inequality. Now again, if we look at the rational numbers, we can complete with respect to these norms. If we complete with respect to the Archimedean norm, we get the real numbers. When we complete with respect to the p-adic norms, we get p-adic numbers. So this is one way, kind of analytic way of introducing p-adic numbers. And again, you can do similar process of completion, which we call localizations for varieties in algebraic varieties over rational numbers, so in higher dimensions. And starting with a variety like that over rational numbers, we get or real variety, or we get variety over p-adic numbers. And now it's a standard technique in arithmetic geometry to study global phenomena by this kind of localizations. Now the real world and the p-adic world are very different worlds. So if you look at primes p, they are small in the p-adic norm, but they tend to be big in the usual norm. And the real numbers are connected, and p-adic numbers are totally disconnected. So we have these dichotomies. On the other hand, very often we look at what happens over real numbers, and we try to find p-adic analogues of these objects. And this is what I want to talk about today, that is p-adic analog of some elements of Hodge theory. So I mentioned here the analytic definition of p-adic numbers, but we can also look at them algebraically. So we have the integers in p-adic rationals, which are element of norm at most 1, and those can be written as projective limit of Z mod Ps, so very algebraically, and then rationals are just obtained by inverting P. So this is very useful from the point of view of arithmetic geometers, because we can work analytically with varieties over rational numbers or using functional analytic techniques, or we can work algebraically with them. I will need to talk about Galois groups. So if you attach roots of polynomials over p-adic numbers, you get QP bar, the algebraic closure. It's now of infinite order. The Galois group is going to be an infinite profinite group, sorry. The algebraic closure QP bar is not complete, so we complete it because we prefer to have completed objects. And the continuous automorphism group of CP is going to be the same Galois group. Now I want to mention something which goes back to Tate to around 1967. Tate's heuristic. So we know that for abstract reasons, CP and C are isomorphic as fields. However, if we want to think about Hodge theory, p-adic analog of Hodge theory, we would like to have p-adic analogs of periods. So typical period is 2 pi I, and the question Tate was asking was, what is the p-adic analog of 2 pi I? In particular, can you find it in CP? And the answer to this question is negative. So let's take a look why. So first, naive argument here. I wrote some formulas. So when we think about 2 pi I, the p-adic analog, we can think that it should satisfy this formula I wrote. So for any n, we should be able to write it as pn log of a pn root of unity. So this log is a p-adic logarithm. It's defined on an open ball of radius 1 around 1, and it's actually a group homomorphism. So this log you see there is actually 0, so no, this is not going to work. So that was very naive heuristic, but less naively. So we are going to have an element, we are looking for an element in CP, right? But CP has Galois action, so the question is under how should this element 2 pi I p actually transform under this Galois action? And if you look at this formula above, you could easily figure out that the sigma in your Galois group should ask by the cyclotomic character evaluated at sigma, and cyclotomic character is the one you get by acting on roots of unity. So Galois group transforms one root of unity to another root of unity, and this way you get this character of sigma values. But now, so now you are looking now for elements in CP which are transformed by the cyclotomic character under the action of your Galois group. And now if we look whether such elements, Tate asks whether such elements exist, and he proves such elements do not exist. So we don't have p-adic 2 pi I. Okay, so this was the introduction to p-adic numbers. I wanted to say a few words about that. Now let's pair it with elements of review of elements of classical Hodge theory, which you would like to find analogues of in p-adic Hodge theory. So first are the period morphisms. So let me start again with a global setting. So I take an algebraic variety smooth projective over rational numbers. I take the associated complex, real manifold, sorry. Look at the C points and take think of it as a real manifold. Then we have a theorem of the Rham, which tells us that singular homology built from n-dimensional cycles pairs with the Rham cohomology defined by smooth differential forms. And this pairing is by integration, so familiar pairing. And this pairing is non-degenerate. So we can try to write it dually. So you see here on the right, we write it as the Rham theorem. Now I have the Rham cohomology again. It goes to degrees up to degree 2d. D is the dimension, and here I wrote my dual of singular homology. I wrote as the Betti cohomology, so it's the dual, and I also took out the C coefficients, so I wrote rational coefficients and took C out to kind of mimic what happens later. And now Grothendieck tells us that since we started with an algebraic variety, we can actually compute this smooth the Rham cohomology with algebraic the Rham cohomology, which just takes algebraic differentials, forms the Rham complex algebraic differentials over the field we started with, so over Q for us here forms complex and takes it Zariski hypercohomology. Okay, so the way I want to put a slogan, I want to state a slogan here, so that let's think that complex numbers now contain periods of all varieties. So what are the examples of periods? So let me mention a couple here. So if we start with a torus, so affine line minus 0, punctured affine line, I can take the unit circle, integrate dz over z around it, and I get the period 2 pi I, so very familiar period. Another example I have here is an elliptic integral whose values is some kind of formula involving Euler gamma function. This is not quite visible from the way it's written, this integral, but it's actually a period of the elliptic curve of the form you have seen before, y squared equals x cubed minus x. So these are some classical periods. And the last, so we have periods which we would like to find in p-adic Hodge theory, and let me just state that complex Hodge theory gives you Hodge decomposition, which I wrote here, so that Betti cohomology with coefficients extended to complex numbers now splits as a direct sum of Hodge groups. So this is another theorem that we would like to mimic in p-adic Hodge theory. Okay, so let's look what can we do in p-adic for varieties over p-adic numbers. So we have this pairing over complex in the complex situation between the Rham forms and cycles, which gives us a period isomorphism between Betti cohomology and the Rham cohomology. So now we start with algebraic variety. So we pass to the p-adic situation. And the first question, of course, you have to address is that the object here on the right is of topological nature. So we need an algebraic analog of this object. We extend coefficients here from rationals to p-adic numbers, so we localize. And then if we do that for Betti cohomology by Artin, we know we can express it as étale cohomology of X with coefficients extended to QP bar. And now this cohomology here is defined algebraically. So we have a good algebraic analog. So in this particular case, this cohomology is actually easy to define. So locally, we have k-pi1 lemma. So actually, this étale cohomology is just cohomology of the fundamental group of your variety. So object which at least you can define very simply. And now this algebraic fundamental group is a profinite by definition, basically profinite completion of the classical fundamental group. Other properties here I mentioned is that what we get are groups of finite rank, because actually they are of the same rank as the Rham cohomology. But there is one more thing happening here, because your variety was defined over QP, or in fact over rationals. You have Galois group which acts on these coefficients, and this action transfers to the whole étale cohomology. So you have an action of Galois group. You have a finite dimensional representation of your Galois group. And so this is important, and we've seen in the previous talks, for example, that this action leads to information, gives information about the rational points of the variety, among other things. So let me take a look at what kind of, I have two examples here I wanted to mention. So what kind of representations we get from cohomology. So one I already mentioned, it's a Tate twist, which is obtained by taking roots of unity, towers of roots of unity, and acting by the cyclotomic character. So shifting them around, which is just an action by the cyclotomic character, and you take some powers of that or some negative powers of that. And cohomologically, because we are interested in Galois representations on cohomology, so cohomologically this representation is just H2 of the projective space, but taking dual. So that's one example. And what you might notice here is that roots of unity are just p-n torsion points of the multiplicative group, so GM. And now, if you look at the elliptic curves, you can do something similar. You look at the Tate module. So you look at p-n rational points of your elliptic curve. Now you have an action on that, as you have seen before. We get a two-dimensional representation. And this representation now, again, has cohomological nature, namely is dual of H1 étale of these elliptic curves with values in QP. So both of these familiar representations, which you have seen before, arise from cohomology, actually, étale cohomology. Okay, so what are the main questions of geometric p-adic Hodge theory? Why do I say geometric here? Because I refer to p-adic Hodge theory, which is concerned with the study of Galois representations arising from geometry. There is an abstract part of p-adic Hodge theory which is very important, but this is just a study of abstract Galois representations. Okay, so what do we want to find in p-adic Hodge theory? So the first point is that we want to find a ring B, which we call a ring of periods, which should contain periods of all varieties defined over QP, and there should be a pairing. between the Rham cohomology and étale cohomology with the coefficients in this period ring, and this pairing, the isomorphism here, the morphism should be an isomorphism. Moreover, that's not everything. That's the easier part. The more difficult part was that we would like to recover, this isomorphism should be strong enough that you can recover one cohomology from the other. In particular, you should be able to recover étale cohomology with the Galois representation from this the Rham cohomology. Okay, so we have these questions, and now Tate tells us, as I have shown you just a moment ago, that B cannot be simply CP, right? Because CP does not contain 2 pi I. So the naive solution to defining B is, okay, well, CP doesn't contain 2 pi I, so you just attach 2 pi I. So we construct this ring, which I will call here B Hodge Tate, where you naively attach, as kind of polynomial, you take a direct sum of CP twisted by n. So these rings have to have Galois action. We discussed that 2 pi I should be acted on by the cyclotomic character. So you just attach twists of CP with its natural action, and it's twisted by the cyclotomic character. Okay, so this doesn't quite work. But it's a good attempt. And in around 1988, Faltings proved what was a big theorem, that if you start with a variety, I restricted here to finite k to finite extensions of QP, there exists a Galois equivariant period isomorphism between étale cohomology twisted by this period ring BHT, and not the Rham cohomology as we wanted, but its graded form, which is the Hodge cohomology, which is just the direct sum of Hodge groups. And now, if we take graded 0 of this graded isomorphism, we actually get what we call Hodge-Tate decomposition. So you get a Galois equivariant isomorphism between étale cohomology and Hodge cohomology, where notice that étale cohomology has to be twisted by CP, and also all the Hodge groups here are also twisted by some cyclotomic characters. Okay, so we got something, not quite what we wanted. So let me comment on, so this proof and this theorem were extremely important for the development of p-adic Hodge theory. Let me mention a few words about this, why is it the case. So this Hodge-Tate decomposition, of course, is an analog of Hodge decomposition. What is important that is this isomorphism is Galois equivariant. So we don't say that we recover this group from this differential data, but what we recover this Galois representation twisted by the canonical representation here from this differential data twisted by this Tate twist. So you can say that this theorem tells us that if you start with this geometric Galois representation, twisting by CP trivializes. We get only Tate twists, and multiplicities of Tate twists, which you see here, are controlled by the Hodge numbers. So this is actually surprisingly strong result. P-adic Hodge theory from the very beginning had very strong applications, powerful applications in number theory, and you see very strong results in number theory being proven actually by just this implied by this theorem. And actually, I always found it rather difficult to understand, because from a point of view of kind of geometric p-adic Hodge theorist, it seems strange that such a weak property as being of representation as being Hodge-Tate, meaning that it satisfies this type of isomorphism, has such powerful repercussions in number theory. But this is the way it works. So the reason it works like that is because we can do a lot of deformation theory, for example, and reduce problems to simple ones. Okay, another thing I wanted to mention about this proof. So this Hodge-Tate comparison theorem of Faltings was a first paper in the series, really, kind of first general paper in his work on p-adic Hodge theory, and it contained basically all the foundational material in his approach to p-adic Hodge theory. That's where Faltings developed almost étale techniques in p-adic geometry, techniques which we use in arithmetic geometry of p-adic algebraic varieties to this day, and very fruitfully. Also there, he had to somehow get around the fact that we don't have resolutions of singularities in these settings. So he developed some approach in which he used modular spaces of curves, and that inspired de Jong to do his alterations later on. So the paper was very influential, but it didn't give us pairing between étale and the Rham. So instead we got a pairing between étale and something, an object which is a graded the Rham cohomology. So the next approach you would think to improving the definition of this ring BHT, Hodge Tate, would be to define a filtered ring, filtered by powers of 2 pi I, whose graded pieces are this BHT. And this is what Fontaine did. So Fontaine defined ring B de Rham plus, and which contains element T, which we now call Fontaine's 2 pi I, p-adic 2 pi I, on which Galois group acts by cyclotomic character. Now this is a filtered ring, so its graded pieces are just this again Tate twist, but these morphisms here, they don't split in any reasonable way. That is, this isomorphism here I wrote, it's algebraic, but it's not Galois equivariant, it's not topological. So it's a more complicated ring. However, Colmes observed that CP itself arises as p-adic completion of QP bar, so that we know. And Colmes observed that B de Rham plus itself can be also obtained as a completion of QP bar, but this completion involves some iterated procedure, iterated derivatives. However, you can still think about this as a completion. And now we have a next theorem of Faltings, which tells us that in fact this ring now contains all periods of algebraic varieties over QP. Well, not this ring itself, but if you attach maybe 1 over T. And so let me state it as the Rham comparison, known as the Rham comparison. I stated in the most general form, which Faltings did not prove, but we know it's true now. So we have a pairing between the Rham, isomorphism between the Rham cohomology and étale once we extend to this big ring B de Rham. And now it commutes with Galois action, but also the filtration. So we basically obtain what we wanted, and the filtration here, at least in the smooth and proper case, is just obtained by filtration by differentials of degrees at least I. In general, you have to use Dalin's approach to define these filtrations. And one more point I wanted to make about this isomorphism is that if you take Galois fixed points of both sides of this isomorphism, you recover the Rham cohomology by this formula from étale cohomology. So you can also say that here we have trivialized the Rham filtration, so to speak, because you get filtration, the Rham filtration here just from the trivial filtration by the powers of T on this B de Rham ring. So this is also kind of quite curious. But we didn't get what we wanted in the second desiderata for p-adic Hodge theory, namely from this isomorphism itself, we don't know how to recover étale cohomology here from this side. And the reason is that this side is very poor in structure. So all we have is Hodge filtration. It's not enough to recover highly complicated Galois action on the right-hand side. So we have to do better. And when I was starting as a graduate student, we were reading all these definitions of more complicated period rings that Fontaine was coming up with. So he was defining he was defining B-Cris, which was supposed to capture periods of varieties with good reduction, then BST varieties of semi-stable reduction, and then they were equipped with various additional structures. So like B-Cris had Frobenius, BST was also equipped with a monodromy, which comes from singularities of the reduction. And maybe to describe the definitions of the process of defining these rings, here I would like to quote Mark Kissen from the Gazette, who said it very well. So one day he asked Fontaine how he had come to invent these period rings. Well, I was doing calculations with Witt bivectors. So it really happened that way. There were a lot of bivectors there. And then he continues, here he had invented these remarkable rings, which had almost magical properties, a theory of p-adic periods much richer than anything one could hope for from its complex analog. Yet the genesis of this was not some pure thought, high-level heuristic about motives a la Grothendieck. It was a long series of intricate calculations from which these remarkable conjectures and theorems were finally distilled. These p-adic Hodge theories seemed to me like an order of monks who were able to reveal the hidden design of a tapestry by examining it one thread at a time. And it very well describes the work of Fontaine. I remember very well these Witt bivectors. So Fontaine, of course, was motivated by the study of p-divisible groups. That's the way he started. And these rings were, so there was some approximation procedure happening. They were of different forms, and not all of them survive. But the ones I put out here did survive. And now, in hindsight, we know that all period rings, at least the first generation, or what I'm describing as the first generation period rings, they are actually cohomologies of geometric points. So you can think of B-Cris plus, so the plus part of B-Cris as crystalline cohomology, so it's some kind of, in this case, it's actually even close to the Rham cohomology of the integers in QP bar, so ZP bar mod P made rational. And B the Rham plus, Hodge completed. Here it's derived the Rham cohomology of the same ring, and also Hodge completed. So this intuition is very good if you do p-adic cohomologies, because it does relate to Kinet formulas and to other formulas in p-adic geometry. Okay, so once these rings were defined, Fontaine and actually Fontaine-Janssen formulated a semi-stable comparison theorem, which now links étale cohomology. So this is the object on the right-hand side. And here you would like to put the Rham cohomology, and this is basically the Rham cohomology. This is some avatar of the Rham cohomology, such that we actually equip it with Frobenius, monodromy, some residual action of GK. So in some earlier papers on the subject, people call it the hidden structures on the Rham cohomology. So they're non-obvious, but they come from arithmetic. So Frobenius here comes from reduction mod P, so your varieties will have reduction mod P, and of course in characteristic P you have Frobenius, so this cohomology was defined so that it actually allows for this Frobenius to be seen on the Rham cohomology. Then monodromy. Monodromy comes from the philosophy that there should be a potentially semi-stable model of your variety. Well, we don't have it actually, but on cohomological level you can see it. And so you can see this monodromy, so you can pretend you have a semi-stable reduction, almost potentially. And this Galois action residual remembers that you have to extend the field of definition to actually have that semi-stable reduction. So this kind of hides the geometry, maybe ideal picture of geometry, which we don't have, but amazingly on cohomology level you can actually see it. And if you use alterations, you can understand that. So now this theorem tells you that in fact periods of all algebraic varieties over p-adic numbers are in fact contained on BST modulo this extension by QP bar. And now this theorem is strong enough to recover the Galois actions. So if we take, if we look at this formula here, and now if we take phi and field zero eigenspaces of the Rham cohomology, you actually recover étale cohomology as a Galois representation. And so basically we are saying that to understand this Galois representation here, we have to understand Hiodo-Kato and the Rham cohomology, which is usually not that difficult. Hiodo-Kato more difficult than the Rham. But then what is not easy, you have to understand these operators. That's not easy, and that's often related to the structure of the integral models. And then you have to understand this filtration, which is the opposite. So this part here is related to the p-adic, to mod P geometry. This part here is actually related to the geometry of the generic fiber, and you have to understand how the geometry of the generic fiber and the mod P geometry interact. So that's the content of this theorem. And let me mention a brief. So the proof of this theorem has a long history. It took several years, took many years. And I listed contributions from various people, but I pointed out in the bold print here, Faltings and Scholze. It's because this theorem was proved by several methods. But Faltings developed the theory I mentioned of almost étale extensions, a very powerful theory. And he was the first one which proved a general form of comparison theorem for good reduction varieties, which we called crystalline comparison. And Scholze continued with Faltings' approach and introduced, so Scholze was able to prove a general form of something called almost purity, and that allowed him to push much farther the p-adic geometry as started by the analysis of p-adic geometry as started by Faltings. So let me go back. So I want to say a few words about these proofs, and not too many, but I want to just point out something about the proof. So what are we trying to prove here? Here we are looking at the cohomology of the fundamental group, and here we are looking at differential forms. So how would you relate fundamental group to differential forms? They live in two different universes, right? Already in the first talk, Faltings mentioned the work of Tate, who related the Galois group itself to differential forms. And this is a vast generalization of this observation, this proof. You can think of this as vast generalization. So let me just mention the main ideas which appear there. So in usual p-adic Hodge theory, we would start with exponential sequence. We don't have exponential sequence here, but we have some avatars of exponential sequence. So we are working on some site which is nice for us. It's called pro-étale site, pro-étale topology, and we are interested in the cohomology of this object QPZP of these sheaves. And now we have this period sheaves now. So these are sheafy analogues of our period rings, various types. And so instead of computing cohomology of QPZP, we pass to cohomology of these period sheaves. And then via these sequences, we pass to the cohomology of the structure sheaf, which now it looks like it's simple, right? We want pro-étale cohomology of the structure sheaf. Okay, and a priori, of course, this is not simple, but now we have the Faltings almost purity theorem, which we can use, and this simplifies computations greatly. So let me maybe already put these two on. So how does this work? So we are interested in étale cohomology of the structure sheaf. So in the group cohomology, really, of the fundamental group with values in the functions on some universal cover, on a universal cover of your variety. I put plus here. That just means that I don't invert P. I actually take the integral elements in the ring. Now I assume my variety is smooth, so I can actually replace it with a product of circles. I try to work analytically. And now, if we look at T, at the product of circles, I have a very simple cover of it with the group ZP, transformation group ZPD. It is obtained by attaching P and roots of the coordinate unit. And now purity, Faltings purity theorem tells you that this very complicated cohomology of this very complicated group with values in this very complicated coordinate ring is actually the same as cohomology of this very simple group for this simple covering with much simpler coordinate ring of this covering. This is not on the nose. This is almost isomorphism, which means that it's up to elements annihilated by all torsion powers of P, and so we have to work in almost mathematics here. But this is great progress now, because you replace the difficult task of computing étale cohomology of your structure sheaf with just group cohomology of a very simple group and not so complicated structure sheaf. So this is what almost purity of Faltings gives us. That's one of its amazing powers. So now it becomes simple. So I give you an example of these computations in dimension 1. So now we just have to compute cohomology of ZP with values in these coordinate rings. But now we have this fundamental unit we took here. This coordinate ring is obtained by attaching P and root of that unit. The action of the Galois group is by powers of roots of unity, so it's very simple. So now this complex, so you want to see how to compute this cohomology. So you look at the action on the monomials here, and you see that everything is just expressed by these causal complexes, very simple causal complexes. So now we just have to understand these maps here, these transition maps. And now it turns out that basically everything, when n is equal 0, this gives you the contributions here in degree h0. You get the original functions on the base, so on your original variety. And in degree 1, you get differentials. Only this is a little bit artificial, but you get this form here. You get the functions, and again, so you get another copy of the functions. In all higher degrees, so if you look at the monomials which come from attaching P and roots, you see that basically you vanish, so that there is no H0, and H1 just contributes this torsion, which is very well controlled. I mean, or at least a very well described torsion. So one remark I want to make is that this proof doesn't quite show how the differentials show up. It just shows you that you have a group which looks like a group of differentials. But you can upgrade these arguments. And the differentials now, the way we understand, they come from various forms of Poincare lemma in these settings. And a graded form of Poincare lemma is so-called Faltings extension, which you see a lot in arithmetic geometry these days. So the moral of the story is that, let me go back, in this computations, that almost purity of Faltings allows you to replace a very complicated fundamental group with very simple fundamental group, and similar with coefficients. And then the way we understand it now, you can say, well, this group cohomology now by theorem of Lazare is the same as Lie algebra cohomology of the same group. And Lie algebra cohomology we know is very close to differentials for a given variety. So that's the way we look at this now. Okay, so maybe that's all I wanted to mention about what we call abelian-Hodge theory. But from the very beginning of p-adic Hodge theory, there was also a non-abelian part. So I want to mention two aspects of it. So in the original works of Faltings, already in 86, he was also interested not just in comparison theorems, on cohomology, but also in the categories of coefficients for these theories. So for the Rham cohomology, let's say we take so for local systems, we take flat filtered vector bundles on X. And the question is, what would be the corresponding category or subcategory of local systems for étale cohomology on the left-hand side? And by a recent work of Scholze, we know that this category should be the category of the Rham QP local systems. In the original, so this is very much an ongoing work in this field. So the question is not to characterize just the most general, the Rham local systems, but also the local systems which are suitable for varieties with, for example, semi-stable reduction or good reduction, so crystalline or semi-stable local systems. So this is very much ongoing. Another question you can ask was not concerning the Rham cohomology here, but concerning Hodge cohomology. And you can ask if you, for categorification of these statements, these isomorphisms. So if you look at Hodge cohomology, the coefficients you will think about are Higgs bundles. And now, can we find a correspondence between Higgs bundles and coefficients for the étale cohomology, so QP local systems, in what form and for which subcategories, etc. So this original contribution here was of Faltings in around 2005, and he introduced what we now understand as vector bundles on the pro-étale side, but he called these objects generalized representations. And by the recent work of various people, we know that Higgs bundles and generalized representations correspond to each other. We still don't know much about how QP local systems fit into this story. Okay, so let me mention a legacy of this Faltings approach to p-adic Hodge theory. So I mentioned that he developed almost mathematics. That is, in the original proof of Tate, there was almost a theory of almost étale extensions, but in dimension 0. Faltings brought it to higher dimensions, made it relative. This was systematically studied in the book by Gaber and Romero, and then Scholze vastly generalized that. So Scholze developed a theory of perfectoid geometry. In p-adic Hodge theory, we have seen a lot of towers, of course, throughout the history of the subject, but Scholze made the study of such towers systematic, and then he developed techniques for study of topology and geometry of such objects. And this is now the way we understand the natural framework for Faltings' almost purity theorem. Scholze also proved a very, very general form of almost purity theorem, which actually allowed him to do p-adic geometry in rigid analytic setting. So let me give you an example that perfectoid spaces have a natural tilting operation which exchanges characteristics 0 and p. So here is a picture. If we look at an Fi space over Cp, we take a tower by p power morphism. We get an object at infinity, which we call X. So this is our tower. The bars mean topological spaces. And now if we are here at infinity, we can actually tilt our object to an object in characteristic P, which is a similar tower, but for Fi spaces over a tilt of Cp, which is defined as this limit of Cp under p power map. It's a field of characteristic P. So we go up, we have a perfectoid object here in characteristic 0, but it has the same topology as the object in characteristic P, and now these towers here are via isomorphism because we are in characteristic P, and we get in the end that characteristic P geometry appears as an infinite covering of characteristic G geometry, characteristic 0 geometry. So that's one of the standard techniques for proving theorems now in p-adic geometry. For example, you can prove aspects of the monodromy weight conjecture by passing to characteristic P. Okay, let me just mention applications of Faltings' approach to p-adic Hodge theory and p-adic Hodge theory in general. So from very early on, we had applications in number theory. So, of course, Fermat's theorem, but then more generally modularity lifting theorems. Then Fontaine-Mazur's conjecture, which tells you that if a representation global representation looks like it's coming from geometry, then it is coming from geometry. Then p-adic Langland's program and Bloch-Kato conjectures, which tell you that you can refine conjectures of Beilinson on special values of L functions by specifying also the rational factor. In commutative algebra, we have the solutions of homological conjectures, the direct summand conjecture. In algebraic geometry, in mixed characteristics, these are very recent developments. We have minimal model programs, vanishing theorems in mixed and characteristic P. And here the main slogan is that the almost purity theorem plays the role of resolution of singularity in characteristic P and mixed characteristic, which we don't have. Thank you very much.
Thank you very much, Wieslava. There is open for questions or comments from the audience.
Are you willing to say just a bit more about the applications in commutative algebra, homological theorems?
I just wanted to say a few. I mean, I just mentioned it because I wanted to mention that this the philosophy that almost purity allows you to overcome the lack of resolution of singularities in characteristic P and mixed characteristic, and for us who work in p-adic Hodge theory early on, you see that you will always hit a wall, and the wall would be always of the same shape, and that is, it will be always defined by lack of resolution of singularities. And now, philosophically speaking, the almost purity allows you to overcome it. So if you go to these huge towers, huge coverings, some maps become flat in the process, for example. So this is the type of techniques which were used in the proof, for example, of the almost direct summand conjecture.
So you mentioned a little bit about this characteristic P geometry and then characteristic zero geometry in the end. So does that mean this p-adic Hodge theory has an analog over characteristic P?
The short answer is no. But
so I have all these comparison theorems, so there's no analog for characteristic P?
So I don't know what it would mean, because p-adic étale cohomology, which is the analog of Betti cohomology, in characteristic zero behaves like, well, in some ways, it behaves like Betti cohomology, so it behaves like classical cohomology. On the other hand, if you take p-adic cohomologies in characteristic P, they don't behave like that. P-adic cohomologies in characteristic P behave more like coherent cohomologies, actually. So the question, if you ask about comparison, then so on one hand you would have differential forms, on the other hand what? Because you cannot take just étale p-adic cohomology. It would have to, I mean, because of it just doesn't behave right. It's all wrong. So I'm not sure.